Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Inshallah today we are going to continue our lesson on chapter 8, Induced Voltages and Inductance. With referring to the textbook, this is actually chapter 20, where your syllabus are subchapter 20.1 up to 20.3, 20.5 and 20.7. So for 20.1, first thing first you need to know is about magnetic flux. On previous topic, chapter 7, you've learned about what is magnetic material, magnetic field, magnetic force, right? But then there is one detailed things that madam has not explained to you is actually about magnetic flux. So similar approach to electric flux. Magnetic flux is actually representing the strength of the magnetic field within or per unit area specifically. Okay, so if let's say you have this cross section of area or loop, okay, the number of the B lines penetrates this loop of area A, okay, specifically with the reference of this, let's say 1 meter square. Okay, if you refer situation A, you have hundreds of field lines penetrate 1 meter square, in comparison to a second situation where you have 1000 of field lines penetrate 1 meter square of area. So the strength will be different, right? So that is explained by the flux. So basically flux is how good, how big the strength of the B penetrates a specific amount of area. That is actually flux. Okay, so the way the B penetrates the flux must be consistent. We must refer to a standard setup, right? So the B that countable, that considered or considered as the one that we going to calculate is the B that perpendicular to the area of the loop. Okay, the B must be perpendicular to the area of the loop. So to make it easy for us, okay, either we're going to use the B perpendicular or resolve the B, or we can also resolve the A, okay, by using or by figuring out where is the normal line of the A. So here is the normal line of the A, normal line. Alright, so the angle also the same lah, means the angle between, if you resolve the B, okay, you're going to use this data, right? Okay, to make the B perpendicular to the plane, or you resolve the plane, okay, make it perpendicular to the B, either one, right? So this is 3D view, XYZ. This is XY view, let's say. So the original B penetrate the loop. This is the loop, the having area is here, right? So this is the original B penetrate the loop of area A. Okay, it is not perpendicular, is having certain angle to the normal line. Here is also the normal line that having, the name of it also normal, right? So it has 90 degree to the A. Here is the A. Alright, so to resolve the B, you have to make use this angle information. So whether it's sin or cos depending on the angle given, right? Make sure the B is perpendicular, or the normal, the area is perpendicular to the B, either one, right? So that is on how to have magnetic flux. So how to make it perpendicular or not, right? So we are going to use, okay, the formula of B flux, symbol of the flux, this is a symbol, is equivalent to B A cos theta. Theta is the angle between the normal line of the A, okay, with the B that penetrates the loop area A. Alright, so for this case, for figure A, right, alright, the B is the blue lines here, right? This is the loops, okay, that place within this B, alright. Where is the normal of the loop here? So the normal of the loop here is actually here. This is the normal line of the arrow, and the B is in this direction, right? So the angle between the B and the normal line is actually 90 degree. So cos 90 equivalent to 0, causing the flux equivalent to 0. So the flux units is Weber, yeah. Okay, it's Weber. And then here the angle is 90 degree. Why is it so? Because the normal of the area to the B here is 90 degree. Okay, and cos 90 is 0. Okay, in simple, there is no B lines penetrate the area, right? That is why the flux becomes 0. Okay, so now let's proceed to B, right? So this is the B and this is the orientation of your loops. Okay, first thing first, let's check the normal line of the loop. So this is the normal line of the loop. The normal line representing the normal line of the area lah of the loop. Okay, and the B in this direction. So, or in this direction. So the angle is 45 degree. Right? So the angle is 45 degree. So you put it here cos 45. So cos 45, the flux of the B is not 0. Bigger than 0. Some amount lah, means it must be some amount. How about this one? Okay, how about this one? This one, this is also the normal line of the loop. Okay, with area A. This is also the line of the B. So the angle is 0. When you put here cos 0, it gives you maximum value, which is whatever the value of BA times of it lah, multiple of it or product of it. Alright, so you will get maximum value of it. Alright, so this is about flux. So you have two choice actually, whether you're going to resolve the A, figure out the A perpendicular to the B, or you resolve the B, make it perpendicular to the A, either one. But basically the idea is the same. You're going to use the same formula, which is BA cos theta. Okay, in terms of mathematics, why is it cos? Actually, B flux is actually a product of B dot A. So this is actually referring to the mathematical treatment of process lah. Right. For question number 4, this is taken from ebook, which is from previous ebook. So a bit changes compared to your textbook. This one supposed to be 0.3 Tesla, right? According to your text. A magnetic field of magnitude 0.3 Tesla is oriented perpendicular to the plane of a circular loop. Calculate the loop radius if the magnetic flux through the loop is 2.7 Weber. And then B, new magnetic flux if the loop radius is doubled. So to solve part A, alright, we know that the angle between the normal line, okay, and the magnetic field, okay, is actually 0 because they are perpendicular coming from the statement given to us. Right? Therefore, to calculate the flux is equivalent to BA cos theta, where our B here is 0.3, our A here is pi r squared. Okay, why is it pi r squared? Because it's a loop, okay, a circle. Then cos 0 degree, which give you 1. So you will get your flux here equivalent to so your r, the radius there, okay, is equivalent to square root of 2.7, okay, divided by pi times 0.3, right? Which finally give you answer of 1.69 meter. For part B, when the radius of the loop is doubled, the area will be increased by factor of 4. Okay, why is it? Because the area is equivalent to pi r square, isn't it? So the r is double, is already become factor of 4. Therefore, your new flux now, okay, new is, and then your flux original times 4 of the original. This is B new, which equivalent to 4 times, okay, 2.7 Weber, which give you 10.8 Weber.